We have seen in a previous video that we could put detailed design inside an engineering template so that we can automatically generate it in our project. We can embed a lot of different information inside those templates, such as formworks for construction, drawings that will morph at instantiation, or, as we will see in this video, simulation preparation data, so that we can directly run a simulation analysis on the instantiated data. This is based on the civil engineer role, CIENC, and the structural analysis engineer, SYE. During the video, we will set up the template and we will reuse it in the next tutorial. In this example, following the steps described in previous tutorials about UDF, user-defined feature, and engineering templates, I create a concrete slab and 4 girders. They have been put in a user-defined feature and are driven by parameters. In the same assembly, I created the detailed structure with one type part for each element, and I assign materials. Those materials have simulation properties assigned to them, such as hook modulus or Poisson ratios, but could of course have more than that. If I want to perform a simulation on this data, I will have to simplify it. For this, the analyst has the capability to create an abstract shape that will contain all his simplified data linked with the designer geometry, but without having to take ownership of the design part. The app simulation model preparation is dedicated to make the design data ready for meshing by defeaturing the design or generating simplified geometry. As an example, I will create a mid-surface of the slab. A link to the design is automatically created with the designer data so that the mid-surface updates if the solid is changed. Same way, I create mid-surfaces for each girders. Since the girder is composed of several faces, I will trim all the pieces together using the trim command with the pieces mode. I trim the same way all the girders. It is always better to rename properly your features. Those mid-surfaces will be used for finite elements, so a good practice is to publish those to maintain a robust link. I can now create a finite element shape that will point to the abstraction shape I just created before. I can now define a surface quad mesh on the slab mid surface with the desired mesh size, here 300 mm, and I mesh it. Same way, I mesh all the girders mid surfaces. I can then assign properties to those meshes, that means a shell section. The support is the publication of the mid-surface of the slab. For the definition of the thickness, I can either input a thickness manually, but this means it will not be linked to the design, either pick the from solid option that will retrieve the thickness from the design part. Then I can define the material by using the in-session mode since they have already been attached by the designer. Same way, I create properties for the 4 girders. Next step is to tie together the slab with each of the girders. I pick the publication of the slab mid-surface and of the first girder. To make sure it is tying only the nodes of the upper flange of the girder with the slab, I add a position tolerance equal to half the upper flange thickness. A tie connection has been created. Operations are repeated for the 3 other girders. Now, I would like to define a group of nodes for the girder that will be attached to the piers. I copy-paste as result the deck start and end axis systems. To drive how many nodes I want to clamp, I can drive the mesh size through a parameter. I create a parameter of length type called mesh size and link the mesh size of the surface quad mesh to this parameter using a formula. I update the other meshes with a formula. This operation could have been done at the creation of the surface quad mesh. This way, by changing a single parameter, I can change the size of all my meshes. Now that I can figure out easily the spacing between the nodes, I go back to my abstract shape and create two planes offsetted from each side of the deck by a value slightly bigger than the mesh size. This will capture the two first rows of mesh nodes. Since I want to capture only the nodes at the bottom of the girder, I will translate the mid-surface by a value calculated from the design parameters. Girder height and so on, so that this will be updated if the design change. Last step is to split this translate by the offsetted planes created before. Going back to the mesh, I will create a proximity group. This group will pick all the nodes close to my split surface. Now, I have isolated two groups of nodes at the beginning and at the end of the girders. I can save my template. Any change in the design, for example here by changing the cantilever between the edge of the slab and the first girder, can be propagated to the simulation preparation data. As you can see, everything has been updated. Mid-surfaces, surface quad mesh, and proximity groups. Now that my template is ready, I can generate an engineering template. Note that this abstract shape and the finite element shapes can be added to the template content. Then I have to define my inputs and publish parameters. Last step is to add this engineering template to my object type where the user feature is already stored. Now my template is ready for instantiation and we will see how to leverage it in the next video.